Hey everyone, in this video we're going to look at transformations of power functions with positive integer index. It's a bit of a mouthful. So what I've created here is a table, first of all looking at when n is a positive integer. So if I just get my pencil, okay, so we're looking at functions, a bit hard to highlight here. But so x to the power of something, but in this case, we're just letting it equal n, but it has to be even positive integer. So even, pretty straightforward, 2, 4, 6, 8. Positive, number greater than 0, and an integer, so it's a whole number. All right, so the example I've got here is a parabola, and you're probably only going to be looking at parabolas or quartics. Okay, so what I've done is I've used the parabola to describe the different transformations, because if you have your rule or your function in this form, then you can read what your transformations are. Okay, so we're looking at a parabola, so just y equals x squared is your basic parabola, but these rules, I use that word loosely, apply for any function where our power is an even positive integer. Okay, so what I've got is a graph of a parabola. The domain is R, so that means x can take on any real value, and your range is going from 0 to infinity. Now, obviously, your parabola can move around, okay? So just make sure that you understand what a basic parabola looks like, and you know what, how the transformations affect that basic parabola. Graphs with an even index, so an even power, look similar to a parabola and have a turning point at 0, 0. So if we're looking at a quartic, for example, it pretty much looks like a parabola. It just kind of has it's a bit of a flatter bottom. All right, so let's look at the transformations column first of all. So f of x equals a times x minus h to the power of n plus k. So n is just our power, but the values of a, h, and k tell us what our transformations are. Now, if it's written in this form, okay, that I've highlighted in blue, and I know you can't see my cursor, so I'll just highlight it again. If it's written in that form, then we can see our transformations and we can see our turning points, which is awesome. Now, if it's not in that form, so let's say we're dealing with the parabola, if it's not in that form, and I've written it down here, you need to complete the square. All right, so you can still graph a parabola if it's not in turning point form, but, and you can still get the turning point, but it's harder to find the transformations. Okay, so what we're focusing on in 3G is actually finding the transformations by inspection, really. Instead of doing mapping, you're able to look at a function and say what the transformations are. All right, so let's go through each dot point individually. Okay, so I'm going to highlight it as we go. So h and k are the coordinates of your turning point. Now, just take note that we do have this negative in there. Okay, so whenever you're dealing with turning point form, if there's a negative there, the value of h is positive. Okay, so we read it as a positive h, not negative h. If it's a plus sign, all right, so if you had x plus h, that's effectively the same as x minus negative h. So h is a negative. Okay, so when we come across examples like that, I'll try to emphasize it. Okay, so HK are your turning point, is your turning point. All right, second dot point, A is your dilation factor. Now, your dilation factor tells you whether your graph goes wider or narrower. Now, your dilation factor can never be negative. Okay, so if you're referring to a dilation factor, you're basically saying what you're multiplying that by, the coordinate by, to make it wider or narrower. Now the negative, so this third dot point, now A can be negative, and that just means there's been a reflection. Okay, so we never say that the dilation factor is negative. Okay, if there is a negative sign in front of your A, then it's just a reflection. Okay, so we don't say the dilation factor can be negative. Okay, it's just whatever A is. All right, sorry, next dot point. H is the number of units translated along the x-axis. Okay, so we've been doing translations now for a while. You know that you can go in the positive direction or the negative direction. So if H is positive, you're going to the right. And if H is negative, you're going to the left. And that's when this is important. All right, but judging you guys over the last few weeks, I feel like you got that down pat. All right, and K is a little bit easier to read because, you know, we've got a plus K. The number of units, you're either going up or down. All right, your vertical translation. Now, the three types of transformations you can have are dilations, reflections, and then translation. So we can have a translation along the x-axis or a translation along the y-axis. The reason I've split them into two is so, I don't know, so you can see it a bit easier going, you know, different graphs. Okay, so first of all, with your dilation. So we're only going to be looking, first of all, with a dilation when A does not, okay, I was just wondering what that says. We're looking at a dilation from the x-axis. So you can say a dilation is from the x-axis, and you can also say a dilation from the y-axis. You can have a combination of both, but if it's written in this form, all right, in our turning point form, then it's probably easier just to say it's been dilated either from the x-axis or from the y-axis. Now, if A is greater than 0, no, sorry, start again. If A is greater than 1, your graph becomes narrower because when you think about it, you're stretching your graph up. So your x values stay the same, but your y values increase. Now, I've got a graph on there, but I might try Desmos. All right, so I've just drawn the same graphs. Okay, so the bluish or purplish graph is my y equals x squared and the black is 2x squared. So I've got a dilation factor of 2. Now, if I just pick a point on my original graph, y equals x squared, and 1, 1 is the easiest. There it is there. Wonder if I can find it. Oh, so close. All right, so just believe me, it's 1, 1. Now, when we're dilating from the x-axis, your x-coordinate change, start again. Your x-coordinate stays the same, but your y-coordinate is multiplied by that dilation factor. So if I'm going up on my axis, on my grid, I should probably say, you can see there's the point 1, 2. So we've gone from 1, 1 to 1, 2. All right, so that y-coordinate is being multiplied by 2. Let's choose another point. I might have to make it a little bit smaller. All right, so 2, 4 is here. Right, another point on the line. So x stays as 2 and y will be double 4. So let's go up and find 2, 8, and there it is on the black. All right, so that's what it means by where it's a dilation factor from the x-axis, but it's affecting your y-coordinate because it's stretching, and don't know why I'm doing this, but I'm doing it with my hands. I'm stretching with my hands and you can't see me. All right, let's go back to the document. Not that one. Okay, so when it's greater than 1, it becomes narrower. So it's kind of going closer to the y-axis. Now, if A is between 0 and 1, it becomes wider. So let's go back to our Desmos screen. Let's make it a little bit easier to see, and let's add 1. So I'm going to do y equals, and I think on our notes we had 0.5 x power of 2. All right, so there you can see in the red, it's become wider. So that means the point, and I'll just get rid of the black one, 0.11. All right, we're still doing it from the x-axis, but it's by a factor of 1/2. So if I go down to here, it should be 1/2, 1.5. Okay, so that's becoming wider. Let's go back to here And just make sure I don't miss anything. Okay, so we just looked at when A is between 0 and 1. And remember, if A was negative, it's going to be reflected. So we'll talk about that in the next column. Now, if A is equal to 1, sorry, I've written here A is not equal to 1, but if A is equal to 1, the graph doesn't change because you have y equals 1x squared, which is the same thing. So when A is not equal to 1, then we say that there has been a dilation of factor A from the x-axis. Now, if you want to do it from the y-axis, it's a little bit more complicated. All right, so I'll just show you on Desmos, and I'm going to go back to that one. All right, so remember our original graph was the purple one, so we had the 0.11, which is somewhere there, and from the x-axis, we're going to go to the 0.12. But if we're going from the y-axis, we're going to look at this point here. So we've got the 0.11, so the y stays the same, but the x changes. And you can see, there we go, it's 0.707. And that is an irrational number. All right, it's just on it to 3 decimal places. Now, if you're familiar with surds, you might know what that number is, especially if you're familiar with trig, but I'm going to show you how to get this value. All right, so we know it's approximately 0.707. All right, going back here. All right, so your formula, I might do that in a different color. I like doing it in orange. What an orange? Well, orange isn't very bright. Can we still see that okay? So this formula here, let's highlight the whole thing, is what we're going to use to get our dilation factor from the y-axis. So you take your value of A. So in the Desmos example, our value of A was 2. Okay, so we're going to use the same value. So we're at 2 is equal to 1 over your dilation factor, which is what we're solving for. All right, so A is a dilation factor from the x-axis, but for this part here, we're finding the dilation factor from the y-axis. All right, so that's what we've got to solve for, dilation factor. Now I'm going to just call it df. You can call it whatever you like. Probably wouldn't use x or y just in case we get confused with our axes. So I'm just going to call it df. And that's to the, no, that's supposed to be a bracket, and now it doesn't look like a bracket. So I'll just put df in brackets to the power of n. So because we're doing a parabola, our value of n is 2. All right, so x squared, n is 2. Now we've just got to solve for our dilation factor. All right, so when your unknown is on the denominator, you can actually just switch these. All right, so we've got dilation factor squared is equal to 1 over 2. Now, I've jumped a step if I was to solve that algebraically, but especially when we do trigonometry, you should just know if your unknown's on the bottom, then you just switch them. All right, so I need to get rid of this squared. So I'm going to take the square root of both sides. All right, I can take the square root of the whole thing. All right, so your dilation factor is equal to the square root of a half. Now, we shouldn't leave a surd like that. Square root of 1 over square root of 2. Hopefully you remember your surd laws. Square root of 1 is just 1, and then we've got over root 2. Now, you can rationalise the denominator. I wouldn't be too fussed for now, but if you were going to rationalise the denominator, so usually we don't leave a surd in the denominator, so that's going to be the same as root 2 on 2. Now, if you remember your exact values from trigonometry, you would have seen that before and realize that it was 0.707, blah, blah, blah. The blah, blah, blah being the decimal places. So on your calculator, you can see I've already done it before. So 1 over square root of 2 is 0.707. If you wanted to do it the other way around, so the square root of 2 on 2, whoops, same thing. All right, so what we'll say for this one here, for this particular example, if you had y equals 2x squared, if you're just looking at the dilation factor, it's been dilated by a factor of 2. From the x-axis, so that's what you would say if it was from the x-axis, or, so not as well, or if you wanted to say it was from the y-axis, dilated by a factor of root 2 on 2 from the y-axis. Now, see how it's usually easier to say from the x-axis, but you do also need to know how to say it from the y-axis. So that what I've highlighted there in orange, make sure you understood how I use that. All right, because you can't always say from the x-axis. I mean it's the most logical thing to do, but you'd hate to get like a multiple choice question that asks for the dilation factor from the y-axis and you're like, I don't know. So you do need to know how to do both. All right, let's move on to reflections. Get my blue highlighter back. All right, so a reflection now with a parabola, if we were to reflect it along the y-axis, it hasn't actually moved. Well, it has moved, but it's the same thing because it's symmetrical around the y-axis. So when a is greater than 0, so when a is positive, the graph is positive. Okay, so we can see there in the black, it's a positive parabola. When a is less than 0, which is negative, the graph is negative. All right. And when it is less than 0, we say it's been reflected in the x-axis. Okay, so you can see there in red, it's been reflected along the x-axis. Now you could have a reflection in the y-axis, but because you're graphing to an even power, it doesn't make any difference. Now, if you had multiple transformations, that's when reflections do count. So if you were translated, so if we shifted our y equals x squared to along 5, so its turning point was now at 5, 0, and then you reflected it, that turning point would then become negative 5, 0. All right, so just down the bottom I said, for these graphs, a reflection in the y-axis means the graph has remained the same as it is symmetrical around the y-axis. However, if a series of transformations were given and translation occurred before the reflection, then you need to consider the reflection. All right, so just being aware, if you were told which transformations to do, so if you did a translation, so you shifted it first and then reflected, then it's obviously going to matter. So I'll just show you here. Get rid of you. All right, so I'll go back to x. Oops. All right, so let's do what I said before. So we're going across by 5. All right, so you've gone across 5, and then if you did a reflection, all right, so if we're doing a reflection in the x-axis, that would be a negative there. All right, so see, flipping over. But if we're doing a reflection on the y-axis, the negative would go in front of the x. So see what's happened there? All right, so that's when it would matter. All right, so the reflection. Now you will notice that you could also say, instead of having a reflection, you could just say, well, it's moved to the right, to the left 5. And we could then get the same thing as if we did this. All right, so it's been reflected. So if you notice how I just changed that up, so I took that negative sign out. So we could say, well, it was reflected and then shifted to the left 5. Okay, and you end up at the same spot. All right. Translation. So moving along the x-axis, I could probably move quickly through this. So just remember your value of h. So when h is less than 0, it's gone in the negative direction. And when h is greater than 0, it's in the positive direction. So just don't get confused with your negatives. So I always, as I said before, find it easier if you've got, say, x plus h to rewrite it as two negatives. So then you know that h is a negative. Because in your rule, over here, that I've drawn some arrows to before, it is a negative. All right, and then along the y-axis, pretty straightforward, up or down. Pretty easy peasy Japanesey. Okay, let's move on to if it was an odd positive integer. So we're going to use the cubic graph now to describe these transformations. So you can see we've got a cubic here. Now your domain and range are both R. And graphs with an odd index look similar to a cubic. All right, and point of 0 gradient at 0, 0. So this point in here. All right, so we're keeping the same form as before, all right, but it just means n is an odd positive integer. Okay, so A is your dilation factor, pretty much the same thing as before, all right, so all these dot points, same as before. Your dilation factor, exactly the same as before. Just remember in calculating your dilation from the y-axis. So let's do an example of that. All right, I might move quickly through it. So if I had, let's say, y equals, I don't want to use 2 again, let's use 3. Oh, I'll use 4. 4x cubed. Okay, it's dilated by a factor of 4. A factor of 4 from the x-axis. All right, so let's just get our decimals back up. All right, so this time we're doing cubed. And what are we doing? 4x cubed. And I might zoom in so it's a little bit easier to see. So the 0.11 is here, roughly. All right, and then 4x cubed. So we're going from the x-axis, so that means our y-coordinate is being multiplied by 4. So if I go up, we should find the 0.14. There it is. Okay, so it's been dilated by a factor of 4 from the x-axis. Now let's choose the 0.11 again. Now if we went across horizontally to get to the corresponding point on the black curve, 4x cubed, you can see there it's 0.63. So that's a dilation factor of 0.63 from the y-axis. All right, but that's that could have been rounded, I'm not sure. So let's actually get the notes back up and work it out as an exact value. So your value of A is 4, all right? The coefficient of x cubed is 4. So I'm going to write 4 equals 1 over your dilation factor. So you can call it just D if you like. So I might call it D in this one, D cubed. And then we're just solving for D, our dilation factor. So switch them over. So we've got D cubed is equal to 1 over 4. And then to get D on its own, we're going to take the cubed root of both 1 and 4. Cubed root of 1 is just 1. And then we've got the cubed root of 4. And we can just leave it like that. I'm not going to bother changing the denominator. All right, so 1 over, now a cubed root. So there you can see 0.629. I think we did have 0.63, wasn't it? All right, so going to this point here, not that point, this one up here. Wrong one. Oh, I had it first time, 0.63. So it has been rounded. All right, so your dilation from the y-axis is 1 over the cubed root of 4. All right, so not really the best number to do. That's why we usually say from the x-axis, but there's nothing wrong with writing that. All right, if we're doing it from the y-axis. So, or if we're doing it from the y-axis, dilated by a factor of 1 over cubed root of 4 from the y-axis. Okay, so let's have a look at reflections. All right, transformations are much the same. So reflections are a little bit different with powers. Let's turn my phone off. Powers with an odd integer. All right, so let's have a look at our cubic. So the black curve is our cubic, and then our pink curve is negative x cubed. Now, unlike our parabola, all right, it's not symmetrical along the y-axis, and it's not symmetrical along the x-axis either. So let's go back. All right, so there's our basic cubic, and oops, let's do the same thing. And there it is reflected. Now it's actually the same as if we were reflecting it along the x-axis or reflecting it along the y-axis. So it actually doesn't matter which one you say, all right? Because reflecting it along the x-axis is the same as if you were reflecting it along the y-axis. And the reason for that is because we're cubing it. All right, so I could write that negative inside. Oops, I'll just close my bracket. To the power of 3, there it is. So you can see the black and the red line are the same. So the reflection is the same for the x-axis and the y-axis. All right, so just reading this note below that, for these graphs, a reflection in the x-axis is the same as a reflection in the y-axis. However, this is only true if the reflection occurs before a translation. Okay, so just the order of your transformations does matter. All right, let's do some practice questions. So we're already halfway through, 30 minutes through this video. And I think it's very important to be able to sketch or actually read what is happening. So we're not doing mapping. Now you can still do mapping, but it's probably a good idea just to understand what has happened to this function. All right, to get it from, all right, we're going from a basic quartic, which is y equals x to the power of 4, and we're transforming it to y equals 1 minus x plus 4. Oh, haven't let that happen for a while. 1 plus 4 to the power of 4. Now, this equation, you can, if you prefer, put that 1 at the end. It's a positive 1, so plus 1. All right, so let's identify the features of this graph. So our value of A, which is the number in front of the bracket, is negative 1. Our value of H is negative 4. All right, so we can rewrite that plus as minus negative 4. And our value of K is 1. So for this function, we've had a reflection along the x-axis. H is negative 4, so it's shifted or translated negative 4, 4 units to the left, or to the left. I'm just going to write to the left, but same as in the negative direction of the x-axis, k equals 1, translated 1 unit. Sorry, sloppy writing. 1 unit up. All right, so what we're going to do is look at the basic parabola first. So let's just draw our Oh gosh, terrible axes. Okay, so we're looking at a quartic. So remember, your quartic, or anything with a power to an even positive integer, is going to look like a parabola. So I'm just going to draw a parabola. All right, but it's a quartic. All right, so what is happening, first of all, is our parabola, oh gosh, has been reflected. Okay, so, oh, that's smooth. All right, so there it's been reflected. All right, so I'm just doing each one separately. And then it's going to be shifted to the left 4. So its turning point there was at 0, 0, and then it's going to negative 4, 0. So I'm going to draw that again. All right, then our last one, we're going to do that last translation. We're going to shift it up 1. So the negative 4, 0 is going to become negative 4, 1. We're going up 1. Now, not the most accurate graph, but that's why you've been given several grids, so you can draw what's happened each time. So the first one, we've got just your y equals x to the power of 4. Then you've had your reflection. And then we had the translation along x-axis and translation y-axis. Now, when you do your graphing, let's just double check using Desmos. So I'm going to get rid of these ones. So 1 minus x plus 4 to the power of 4. All right, so you can see there's the point negative 4, 1 that I had. I probably had it crossing the y-axis too early, judging by that. But if I was sketching this in a SAC or on an exam, I would actually find out the x-intercepts. So I'll show you how to do that in a sec, and your y-intercept. Now, let me just go back. Another important feature, which I just realized, is your turning point. So remember, this gives you your turning point. So negative 4, written it there, 1, although the 1 I've rewritten it here at the end. All right, so just rewriting this plus as negative, negative. So you can see there's the coordinates of your turning point, negative 4, 1. So if you're ever unsure, you can always check, all right, is my turning point correct? No? Well, what have I done incorrectly? You also don't need to follow each step. It's just to show you how to get there. What was I going to do before? Oh, yeah. So that y-intercept is definitely not there. Let me just graph it a bit better. That wasn't good at all, was it? It does eventually cross, so I should put it on the graph. All right, so we've got a y-intercept and 2 x-intercepts. All right, so x-intercept, let y equal 0. So what do we got? 0 equals 1 minus x plus 4 to the power of 4. All right, so let's just solving. All right, we can take the 4th root of both sides, so x plus 4. I've taken the 4th root of the left side. Now, if I'm taking 4th root of 1, you're going to have a positive and a negative solution. All right, so whenever you're taking an even root, you're going to have a positive and a negative. So we're going to have x plus 4 equals, so the 4th root of 1 is just 1. So it's going to be plus 1 and negative 1. So when I solve that, I'm going to have x equals 1 minus 4, which is negative 3, and then negative 1 minus 4 is negative 5. So remember, I did that before on decimals. Let's go back here. So there we go, -5, -3. All right, our y-intercept, do I leave enough space? Of course not. All right, so y-intercept, going to let x equal 0. That's going to be a little bit easier. There is only one. So y equals 1 minus 0 plus 4 to the power of 4. Easy if you know the power of 4. But when you're taking to the power of 4, you're just doubling and then doubling again. So double 4. No, we're not. Sorry. What am I doing? 4 times 4. Yeah, so 16 times 16. No. Anyway, let's just 4 times 4 is 16 times 4 is, yeah, I was multiplying by 4 before, not to the power of 4. All right, so 4 to the power of 4, which is 4 times 4 times 4 times 4. All right, so it's going to be 16 times 16. So if you know what that is, if you know your squares up to 16, what is that? Is it 200? Oh, what have I done? 16 times 16, 200 and, I'm getting 296, but I might just do it on the calculator. Sorry about that. Where are we? Okay. 16 times 16, 256. Oh, that's way down. Y equals 1 minus 256, so negative 255. All right, clearly not to scale, so we wouldn't even see that y-intercept, but it does exist, okay? We can't ignore it. It is there. All right, but clearly not on my scale. Anyway, let's move on. So the next one, let's just identify, oh gosh, sorry, it's my hand on the tablet. All right, so identifying your values of A. So A equals -3, H is +2, and K is equal to -3. So I know my turning point is at 2, -3, which is good. All right, so that might help me when I'm doing my graphing. I have a value of, the value of A is -3. So that means we've had a reflection along the x-axis, and we've also had a dilation factor of 3 from the x-axis. All right, so keep that in mind. All right, so we already drew the basic quartic before, so I'm not going to draw it again. So first of all, I'm just going to do a dilation. Factor 3 from the x-axis. Now with your basic quartic, you do have the 0.11. So when you're dilating it by a factor of 3, that 0.11 is going to become 1,3. So it's actually going to become narrower. And remember, in this box, let's go up a little bit more. When A is greater than 1, the graph becomes narrower. So that's what we're expecting to happen. All right, so I'm just going to draw a quartic that's kind of narrow. Okay, then I'm going to do my reflection. So it's been reflected along the x-axis. So this graph just now is upside down. Right, so if you think about this point being 1, 3, and then you've got its corresponding point here, which is -1, 3, because it's symmetrical, then when you reflect it, it's going to become 1, -3, and this point is going to become -1, -3. All right, so I'll just put the reflection here. So reflected along the x-axis. All right. Oh, we're going to keep going. Then we had translation. So it doesn't matter which translation you do first. You can do them both in one go. So translated, what did we do? 2 units to the right. All right, so this point here, which was before 0, 0 at the origin, is now going to be at 2, 0. And I'm just going to sketch that. If you wanted to do the points, you're just going to add 2 to each x coordinate. All right, and then our last one. What has happened? It's gone down 3. Translated 3 units down. Now we should say the x-axis or the y-axis in positive or negative direction, but that takes a lot of writing, and clearly I can't write that well on the computer. All right, so that point 2, 0 now becomes 2, negative 3. So we no longer have any x-intercepts. And remember, our turning point was going to be 2, negative 3. We looked at that before. Now we are going to have some y-intercept, sorry. So a y-intercept when x equals 0. So we're just going to substitute 0 back into our original function. I'll just scroll up so we can actually see it. So y equals, what have we got? Negative 3, 0 minus 2 to the power of 4 minus 3. That's going to be a nice one to do. So we're going to have negative 3, negative 2 to the power of 4. So when you're taking a negative number to an even power, that negative goes. So 2 to the power of 4. So 2 times 2 times 2 times 2 is 16. So it's going to be negative 3 times 16 minus 3. Negative 3 times 16, negative 3 times 10 is negative 30. 3 times 18, sorry, 6 is 18. Negative 48 minus 3, negative 51. All right, so that's your y-intercept. Now, in these examples, I didn't really talk about the domain and range, but your domain is not really affected, but your range does change. So the range, I might just say for this one, is because it's been reflected, we're going from negative infinity up to that turning point, which the y-coordinate is negative 3. Right, and we use a square bracket because it is included. All right, so let's graph this. I wonder if I can just copy and paste it into decimals. Wouldn't that be nice? Do you think it's going to work? Oh, awesome. Okay, so there it is. So there's our turning point. And is it going to tell us our y-intercept? What was it at? There it is, negative 51. How good is that? So, oh, sorry, didn't mean to do that. So there's our sketching our graph. Okay, oh no, I thought we had some axis-intercepts. I was just seeing that grid line. So there's our turning point. See how it's a bit flatter than a parabola would be? All right, but you still have that turning point there at 2, negative 3. All right, let's move on. Can I move on? Computer's glitching. Come on. All right, find the rule for the image of the graph of y equals x cubed under the following sequence of transformations. So we've had a reflection in the y-axis, dilation of factor 3 from the y-axis, and translations. All right, when you're, I prefer mapping because I always feel like you're less prone to make mistakes, but we're not doing mapping in this section. So let's have a look at this cubic, and remember we're going to write it in the form y equals a x minus h, and it's because it's a cubic, I'm going to put a cubed up there, plus k. So all we're going to do is substitute in the values here. So reflected in the reflection in the y-axis. Oh, so we've had a reflection in the y-axis. and our dilation of factor 3 from the y-axis. Now, because it's a cubic, the reflection in the y-axis is the same as if it was a reflection in the x-axis. All right, so we're going to have a negative value of A. Actually, I might leave that for now. Let's look at the value of A. Because we're doing it from the y-axis, so remember our rule for a dilation factor from the y-axis is A equals 1 over your dilation factor to the power of n. So in this case, it's 3. So the dilation factor is 3. So A is going to be 1 over D cubed, which is 1 over 9. All right, so before we had the value of A and we had to find the dilation factor. This time we've been given the dilation factor, so we're substituting that in. So D equals 3. The dilation factor is 3. So 1 over 3 cubed is not 9, Karen. All right, it's 27. Sorry, my bad, 27. All right, so we've got a value of A, and that is going to be negative because we've got a reflection. So A, you can write that in, y equals negative 1 over 27. Now we've got a translation 3 units in the positive direction of the x-axis. So that means h is equal to 3, and k is our vertical translation, so that's 1 up. So k equals 1. So x minus 3 cubed plus 1. All right, so let's put that into Desmos just to check, because it's always nice to check. All right, we'll get rid of u. Let's see if I can remember what it was. Can't remember. Oh, is it coming back to me? Is it 3? Oh, gosh. 3. Okay, awesome. What's 3? 3, and it was a cubic plus 1. Okay. So there's our cubic. Let's just draw the basic cubic just to compare. All right, so there it is. So you can see it's been reflected. All right, but let's have a look at what is happening to a point. All right, because sometimes it's a bit harder to see with a dilation factor what has actually happened. So my blue is my original, so I'm going to choose the point 1, 1. Now that's the point of intersection, so just be careful with that. So there's 1, 1 on my blue graph. Now if we've been dilated by a factor of 3 from the y-axis, that means my coordinate 1, 1 is going to become 3, 1. All right, so I'm going to go across to 3, 1. Can you see it? Oh, come on. 3, 1. All right, so we've gone from the y-axis. Now it's written as 1 over 27. You're probably thinking, what? How do you get 1 over 27? Well, that's also the dilation factor from the x-axis. So remember, you can say it from the y-axis, and in this case we said it from the y-axis, but it's the same as saying, well, it's a dilation factor of 1 over 27 from the y-axis. So this point, where were we? 1, 1, and it might be a bit hard to see. Oh, actually, what I might do, no, I'm wondering, it might be, because we've had translations, let's just get rid of the translations for a sec. Might be easier to see. Oh, see, there's not much space. Right. Okay, there's, oh, I've had a reflection there as well. Let's get rid of that reflection. Might be easier to see. All right, so there's 1, 1 on our original. God, there we go. So our 1 over 27 is from our x-axis. So you can see this will be 1 over 27, which I'm assuming is 0.037. Let's just check on the calculator. All right, so there you go. So in our original graph, though, we were saying from the y-axis. So a dilation factor of 3 from the y-axis is the same as a dilation factor 3 from, dilation factor 3 from the y-axis is the same as dilation factor of 1 over 27 from the x-axis. All right, let's move on. Could be here forever and my computer's glitching, so see how we go. The graph of y equals a blah 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 has a turning point at 1, 7 and passes through the point 0, 23. Find the values of h and k. So fantastic that we've got the turning point, because that's going to give us h and k. So oh gosh, let's try that again. H equals 1 and k equals 7. So we're going to substitute, and we've got this point here, 0, 23. So that means when that point can be substituted in, so x equals 0 and y equals 23. So with my equation, y equals a x minus h to the power of 4 plus k, I can substitute in those 4 values and then find the value of a. So y is 23, x is 0, h is 1, and k is 7. And now we're just solving for a. So let's take away 7 from both sides. So that's going to give me 16. And then I'm going to take negative 1 to the power of 4, which is just 1. So a times 1 is a. So a is just 16. Just make sure I've done that correctly. Sorry, I think yes. So a is 16. Thought it was going to make me do the fourth root of it. Okay, so y equals 16, x minus h, which is 1, plus 7. I've got to put to the power of 4 here. All right, so if you're unsure, just substitute it in either into your calculator or Desmos. So I'm just going to do Desmos 16. Let's get rid of you. All right, so 16 x minus, so 1 to the power of 4 plus 7 minus 7 plus 7, I think. Gosh, I can't remember. 1, 7, 0, 23 doesn't matter, 16, cool. All right, so we should have a y-intercept at 23, so we can't see it at the moment. So there's our turning point. Come on, 1, 7, and come back. There it is, 0, 23. So you can always check on your Desmos. If you wanted to do it on your calculator, probably I should start showing you things on the calculator too. Let's just go to menu and we want a graph. Let's get rid of the ones I've already got in there. Can't really see that, so I'll put it down. So 16 x minus 1 to the power of 4 plus 7. All right, so we can't really see it. If we need to see it, just go to Zoom, quick, standard. Hopefully that works for us. Okay, so there's your turning point. So it won't come up just by pressing on it. So we can go to analysis. Actually, I don't want that one. G-solve. So we want the minimum. You can, for this one, you can either do minimum or function minimum. But I'm just going to do minimum. There it is. There. Don't know why it's very close to 1. It should be 1, 7. And then your y-intercept. There we go. 0.23. So you can get your values that way as well. All right, I think that is it for the notes. Quite a long video, but as always, very entertaining. Bye, guys.